Am I audible to all of you? Audible, guys? All
Yes,
right.
sir.
All right. So, good morning, everyone. Just one moment. Let me fix one more light here. All right. So, good morning, all of you. Today we have the second class of Science and Technology. In the last class, we started our discussion on the topic of nuclear technology, and in the discussion of nuclear energy I told you, just one second, let me see if the recording is on. So in the discussion of science and technology I told you that we started with the topic of nuclear energy, nuclear technology, and in the discussion of nuclear technology we had discussed two forces, gravitational force and electromagnetic force. I have told you that gravitational force and electromagnetic force, both of them are long range forces. That means they become zero only when you pull objects up to infinity. I also told you that what is the nature of gravitational force? It is an attractive force. Electromagnetic force is both attractive and repulsive force depending on the charge and polarity. Then I told you what is the how does the gravitational force manifest? It manifests in accordance to the mass and the distance between the two bodies, and electromagnetic force also manifests in accordance to the charge and polarity and the distance between the two bodies, right? Up till here we have discussed. Now, and you guys can recall that before that we talked about what is the universe ideally made up of. So we came down to a discussion that universe is made up of elements and forces, right? There are total 118 elements in the periodic table, out of which up to 92 elements are naturally occurring, and from 93 to 118 they are artificially or man-made. Got it? And then under forces, there are four types of forces in nature, and these are the forces: gravitational force, electromagnetic, strong nuclear, and weak nuclear forces. I hope all of you guys can recall. Now let us start. Let us go further and discuss the topic beyond this, and please write down strong nuclear force. Please write down, guys, strong nuclear force. The topic is, so these are the four fundamental forces: gravity, electromagnetism, strong nuclear, and weak nuclear. And now the discussion is on. So this is the periodic table, right? Strong nuclear force. Let us start, guys. So as we are discussing the topic of strong nuclear force, Acha, this is my personal advice to all of you. Please make sure that you have attended the previous class, right? First class. You please go in a sequence, because see, although environment was also somewhat like that, but when it comes to science, you may not find a lot of interrelatability between two topics, right? Like once we finish nuclear energy, I may start space technology, and in the discussion of space technology there would literally be no relation between nuclear and space, right? Very few relations will be there. So if you are missing out nuclear energy's first class and you think that you may be able to understand in the second class, it will be slightly difficult. But yes, if you miss out nuclear energy completely and you join the first class of space technology, you will not have any problem, because there is complete, isolation of the topics, right? So guys, see, so this is what we have as periodic table. All of you guys remember what is a periodic table? A periodic table, all of you guys recall, it is the list of, or it is the combination of all the elements that are present on in nature, that right, that are present in the universe, man-made and natural occurring. Got it? Now guys, whenever you represent, whenever we represent any element, whenever we represent any element in the periodic table, let's say for example, can anyone tell me what do you call this element H? We use some alphabetical symbols for those elements, right? What do you call this element H? Tell me.
Okay, okay.
Hydrogen. Got it? So H is hydrogen. Then students, tell me, what do you call this element? He. Helium. Very good. What do you call this element? Carbon. Perfect. What do you call this element? U. Uranium. 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 U is uranium. Then what do you call this element? TH. Thorium. Very good. And lastly, what do you call this element? Pu. It's called plutonium, guys. Plutonium. Very good, Srinath. Right? Plutonium. So what we have is, what I've done here, see, when it comes to the subject of chemistry, when it comes to subject of chemistry and representation of elements, we use some symbols, we use some alphabetical symbols to identify all elements. H is the alphabetical symbol for hydrogen, He is for helium, C is for carbon, U is for uranium. Acha, by the way, uranium is named after the planet Uranus. Actually, the planet Uranus and the element uranium, they both were discovered in the same year, right? So that's how the name of the element was named after the planet Uranus. Similarly, plutonium, named after Pluto. The year when plutonium was discovered, Pluto was also discovered in the same year, right? And thorium is named after Thor. All of you have seen Marvel Comics Thor, not the Marvel Comics Thor, but the Norse god, the Nordic god Thor, right? They are named after like this. So I hope all of you get it. So this is how we represent elements in the periodic table. Now guys, whenever we write these elements like this, we often write some numbers around these elements. Whenever we write these elements, we write some numbers around them. Like for example, for hydrogen, we write a number 1 on the lower corner. It could be written on right and left, doesn't matter. You can write it either on right or left, does not matter, but it is written in the lower corner of hydrogen. Then there is a number we write for helium, it's called 2. For carbon, we write the number 6. For thorium, we write number 92. For uranium, we write number 92. For thorium, we write number 90. And for plutonium, we write number 94. What do you call this number that we write in the lower corner of the elements? This number that we write in the lower corner, we call this number as atomic number. This number is called atomic number. What is the meaning of atomic number? Guys, simply atomic number means it is the total number of protons. Total number of protons present. Total number of protons. Oh, just wait. It is the total number of protons present inside the nucleus of an atom. Total number of protons present in the nucleus of an atom, we call this atomic number, right? We call this as atomic number. That means if you look at the atom, we all know atom has got a nucleus at the center, and around this nucleus it has got electrons, right? The nucleus is made up of primarily protons plus neutrons. All of you guys know protons and neutrons are present in the nucleus, right? So protons, whatever number of protons are there in the nucleus, we write it as atomic number. Okay, so whatever number of protons are there in the nucleus, we write them as atomic number. We call it atomic number. Okay, so atomic number is the total number of protons present in the nucleus of an atom. Got it? Present in the nucleus of an atom, total number of protons present in the nucleus, atomic number. By the way guys, the number of protons and the number of electrons outside an atom is also outside a nucleus is also same, right? Right now we can consider them same. When we study ions and other kinds of things, then it's a different conversation, but you can just remember that number of protons is generally equal to the number of electrons, right? Protons are positively charged, electrons are negatively charged, right? So same number of protons, same number of electrons. So what is atomic number? Atomic number is the total number of protons present in the nucleus of an atom. We call this atomic number, nucleus of an atom. Got it? Then guys, apart from this particular number, there is one more number that we write. Apart from this number that we write in the lower corner, there is one more number that we write, and that number we write in the upper corner of the atom. Like for above hydrogen, we write number 1 again. For helium, we write number 4. For carbon, we write number 12. For uranium, let's take 235. For thorium, let's take 232. And for plutonium, let's take 239. 239. These are the atoms, these are the numbers that we write on the upper corner. What do you call this number that we write at the upper corner of an atom? This number that we write in the upper corner, we call this number as mass number, not atomic mass, mass number. What is mass number, guys? Mass number is basically the number of protons plus neutrons present inside the nucleus. Number of protons plus neutrons present inside the nucleus, we call it mass number. Now guys, this is probably something that all of you know, right? Even if you're not from science background, you probably know this. But if you don't know this, it's perfect, right? Now you guys know this. So whenever we represent an element, whenever we are going to represent any kind of element in the universe, we write elements like this. Atomic number, mass number, right? Atomic number at the lower corner, mass number at the upper corner. All of you guys are able to get it, right? So now let me ask you guys some questions and you guys quickly answer them on the chat, okay? So if I ask you, how many protons are there in the hydrogen atom? Quickly. Or hydrogen nucleus, quickly. Answer them in the chat. 1. How many protons are there in uranium? Uranium protons. 92. That means there are 92 positively charged particles. Remember, what is the charge of proton? Positive. How many protons are there in carbon? 6. Got it? Now guys, my question is, how many neutrons are there in neutrons, guys? Number of protons is atomic number. Mass number is protons plus neutrons. So my question is, how many neutrons are there in helium? Tell me, neutrons in helium. Neutrons in helium. No, helium. Sagar, think about it. Neutrons in helium, it is 2. Because mass number is 4. For helium, mass number is 4. That means protons and neutrons is 4. And protons are 2. So how many neutrons are there? 4 minus 2. Sagar, are you able to understand? How many neutrons are there in helium? 2. Sagar, did you understand this? Right? Alright. Then tell me how many neutrons are there in the case of carbon? Neutrons in carbon. Tell me. 6. Perfect. How many neutrons are there in hydrogen? Hydrogen, how many neutrons? 0. Very good, Srinath. Very good, Sagar. Very good, Shafiq. Very good, Vani. 0. Why? Because number of protons are 1. Mass number is also 1. That means number of neutrons is 0. There should not have any. There should not be any. There should not be any neutron in hydrogen, and that is what we have for hydrogen. So hydrogen has 0 neutrons. And now my question is, how many neutrons are there in the case of uranium? How many neutrons are in uranium? It is, yes, very good, Srinath. It is 235 minus 92. 235 minus 92, that's 143. Perfect. Very good. Very good, guys. So this is what we have. All of you are able to understand. If I ask you how many neutrons are there in thorium? How many neutrons are there in thorium? Come on. ये तो simple calculation है. Yes, exactly. 142. Sagar, are you able to get it? Non-science students? Sagar, did you understand how all these things happen? 142. Perfect. Right? Alright. So this is protons and neutrons. So guys, all of you have understood, whenever we represent an atom, it is expressed in the form of some two numbers, atomic number at the bottom end, mass number at the top end. And both atomic number, mass number are telling us about the status of the nucleus. Like how many protons are there in the nucleus and how many protons plus neutrons are there in the nucleus, right? That is what atomic number, mass number is. Now, guys, let us start with the understanding of strong nuclear force. This particular discussion was needed, only then we could have started strong nuclear force. I want all of you to pay 100% attention and just look at me, guys. Just look at me, just try to visualize whatever I am saying. Mind my words, guys, science requires a lot of visualization. And I will keep on doing these kind of sessions in between so that we are able to visualize what is really happening in the real world around us. So please pay 100% attention here. So guys, let's imagine there is a complete empty space. There is a complete empty space. And let's say we have a hydrogen atom in front of us. We have got a hydrogen atom in front of us. What is a hydrogen atom made up of? Just one proton at the center. Look at hydrogen, guys. Atomic number 1, mass number 1. So what is hydrogen made up of? Hydrogen is made up of just one proton at the center and one electron revolving around it. Will you guys agree to this? I told you number of protons and electrons are same. So one proton at the center and one electron revolving. Tell me yes in the chat. Are you guys able to visualize? So if I try to create a hydrogen atom for you, the proton is at the center and there is one electron revolving around it. All of you are able to visualize? This is typically how a hydrogen atom should look like. Just one proton, positive, one electron, negative. Acha, did you also see one positive, one negative? That means the net charge, the total charge is 0 because one positive, one negative has cancelled out each other. Right? One positive, one negative has cancelled out each other. So the net charge becomes 0. The final charge becomes 0 and the atom is electrically neutral. The atom is electrically neutral because there is one positive and one negative. That is also the reason why atomic number of protons are always equal to the number of electrons, because electrons and protons together create or cancels all the charges of the atom. So atom by and large is electrically neutral. Remember that, right? Atoms are electrically neutral. Got it, all of you? I hope all of you are able to understand up till here. Now guys, let's try to create in the same empty space, let's try to create a helium atom, right? So in case of helium, what do we have? We have two protons. We have got two protons in the nucleus, right? And around these two protons, we have two electrons revolving around the nucleus. Are you guys able to visualize? So two protons at the center and two electrons revolving around it. Are you able to visualize this part? Tell me yes in the chat quickly. Two protons at the center and two electrons revolving around it. Tell me yes in the chat. Right? Perfect. So this is helium. When you try to create a picture of carbon, there are 6 protons. 6 protons are there in carbon, in the nucleus of carbon, and there will be 6 electrons revolving around the carbon nucleus. All of you would agree? 6 protons at the center and 6 electrons would be revolving. If you try to create uranium in your mind, 92 protons, 92 positively charged particles are there, going to come from all ends, and they all are stuck in one single nucleus. 92. And there would be 92 electrons revolving around the entire nucleus. 92 electrons are going to be revolving around the entire nucleus, and that's how the uranium atom appears. I hope all of you guys are able to visualize. So 92 protons and 92 electrons. Got it? All of you? Now, just think about it, guys. For hydrogen, there is no such problem because only one proton is there. But when you look at helium, helium has 2 positively charged particles, 2 protons, and both these protons are living inside the single nucleus. Both these protons are there in a single nucleus. So guys, just think about it. If there is a single nucleus where 2 positively charged particles are there, don't you think these 2 positively charged particles will have a repulsive force between them? Like charges repel. Will you agree, guys? These 2 protons should actually be repelling away from each other. Don't you think so? Tell me, guys. The 2 protons in the helium, they should ideally be repelling. But if you look at carbon, how many protons? 6 protons were there. All 6 of them will try to repel. They will try to rip apart the entire nucleus of carbon. But all these 6 protons are there inside one nucleus, which are all positive. They should have an even stronger repulsive force. And guys, when you look at uranium, element 92, it has got 92 protons. 92 protons means a massive repulsive force. Don't you think so? 92 particles are simply having the same charge. They are trying to rip apart the entire nucleus. But guys, don't you think helium exists in nature? Helium exists in nature despite of this repulsive force in the nucleus of helium. Carbon exists in nature despite of a stronger repulsive force in the nucleus of carbon. And guys, uranium also exists in nature despite of a massive 92 particles trying to rip apart the entire nucleus. All these elements are naturally occurring elements, guys. Didn't I tell you? Up till element 92, all of them are naturally occurring. I told you this in the last class. Up till element 92, all of them are naturally occurring. So remember, guys, uranium is the heaviest naturally occurring element. Uranium, remember that if you are not knowing this, it is the heaviest naturally occurring element. Heaviest naturally occurring element is uranium. So guys, helium exists. 2 protons, they will try to run away from each other, but helium do exist. Carbon, 6 protons, they all will try to run away, but carbon also exists. Uranium, 92 protons, all of them trying to run away, but still uranium also exists. So my question is, how is all these particles having the same charge, having high repulsive force, are able to manage to survive next to each other? How are they able to survive? So the answer is, just visualize, guys, just visualize. If helium is there are 2 protons of helium, and both these protons of helium are trying to run away from each other. They are trying to rip apart. But if I want to create helium in nature, don't you think the nucleus of helium will have to apply an external force? The nucleus will have to apply an external force, only then the 2 protons can be held together. Guys, just think about it. If there are 2 people on earth, they cannot stand each other. They literally hate each other and they are trying to run away. If you want to hold these 2 people, you have to apply some kind of force, some kind of bond. In India, we call it marriage, right? So when it comes to 2 particles which are literally not having any affinity with each other, they are trying to run away from each other. If you try to hold these 2 protons inside the helium nucleus, the nucleus will have to apply an external force to hold them together. The nucleus will have to apply an external force to hold them together. Only then the nucleus will, only then the protons will persist within the nucleus. And guys, this force that is being applied is called strong nuclear force. This force that the nucleus applies to hold the protons in its place, it's called strong nuclear force. When you talk about carbon, how many protons are there? 6 protons. All these 6 protons are trying to run away from each other, but carbon will apply an even stronger force, or strong force lagega. Even stronger force will be applied, and that force will hold the carbon in its place, carbon nucleus in its place. And just look at uranium 92, guys. 92 particles, all of them trying to run away. If uranium needs to exist in nature, then uranium will have to apply a very strong force, very strong. 92 positive particles are held together in a single nucleus. And what do you call this force that the nucleus applies to hold all the protons together? Strong nuclear force. Tell me yes in the chat if you guys are able to visualize. Tell me yes in the chat, guys, quickly. This force is called the strong nuclear force. Sagar, what about you? I think right now Sagar is non-science. What about other students who are not from science background? Vani, you are from science background, right? So you understand. Manoj, Shafiq, I think you are also from science background, if I'm not wrong. Yeah, Srinath, Shritama is also from science background. Nihal, Achintanya, and Bharat Krishna. Bharat Krishna, you are same Chinni Krishna, or you are a different person? Okay, Shritama, you are from non-science. Alright. Srinath is from science. Okay. Alright. So, Nihal is also from science. Alright, perfect. So, Shritama and Sagar, 2 students we have. I hope both of you are able to follow. Any problem you have in between, you stop in there and there. So, guys, let's talk about strong nuclear force now. Let's talk about strong nuclear force. So, we have just tried to visualize that atoms inside their nucleus are going to have positive particles, and these positive protons will have a tendency of running away from each other. But if all these atoms needs to exist in nature, the nucleus will end up having a strong force to hold all these atoms in place, right? A nucleus is going to have a strong force to hold all these atoms in place, and that force is called strong nuclear force. Now, guys, my first question to all of you, Strong nuclear force is the force that is holding all the entire nucleus intact, which is holding all the particles intact inside the atom, inside the nucleus, not the atom. Now guys, tell me, what kind of force will this be? Attractive or repulsive? Remember, it is holding the protons against their repulsive power. It is holding the protons against their repulsion. What kind of force will it be? Just write down A or R. Sagar thinks it is attractive. Shafiq thinks it is attractive. Vani thinks it is attractive. Shritama is also saying attractive. Very good. Very good. Guys, can I say it should be highly attractive? Because it is holding protons which otherwise would have ripped apart, which otherwise would have never stayed inside the nucleus. They would have stretched and ripped apart the nucleus. So guys, we should say it is highly attractive force. First point, strong nuclear force, it is a highly attractive force. Write down guys quickly. It is a highly attractive force. Point number 1. Second point, please write down under strong nuclear force. Second point, it is a force responsible. It is a force responsible for maintaining the integrity. It is a force responsible for maintaining the integrity of the nucleus. It is the force responsible for maintaining the integrity of the nucleus. It is a force responsible for maintaining the integrity of the nucleus. It is a force responsible for maintaining the integrity of the nucleus against the proton-proton repulsion, or you can say against the repulsive forces between protons of the nucleus. Against the proton-proton repulsion of the nucleus. Against the proton-proton repulsion of the nucleus. So guys, otherwise nucleus is actually, it was never supposed to exist. But because the strong nuclear force exists, that's how the nuclear integrity is maintained. And guys, do I have to tell you this? That helium having just 2 protons will require small strong nuclear force. Uranium having 92 protons will of course require a massive strong nuclear force in order to hold itself, right? And guys, please write down the third statement. The third statement is, what is the range of this force? Is it a short range force or a long range force? So guys, I told you gravity and electromagnetism, both of them are long range forces, right? Gravity and electromagnetism, they are long range forces. But when you talk about strong nuclear force, we don't see this force outside the nucleus. Outside the nucleus, we do not experience this force at all. So this force is a short range force, exists only within the nucleus. Please write down, it is a short range force. The range is defined only within the nucleus, guys. Outside the nucleus, it is not found. Himanshu, what about you? Are you from science or non-science background? So when it comes to strong nuclear force, it is a, alright, science, alright, great. So it is a short range force. You can just write down, it's a short range force limited within the nucleus, right? Or you can say found within the nucleus. That is what is strong nuclear force. And now guys, please write down the fourth statement also. Please write down the fourth statement as well, and write down strong nuclear force is the strongest force in nature. It is the strongest force in nature. Strong nuclear force happens to be the strongest force in nature. It is the strongest force in nature, right? Out of all the out of all the 4 forces, electromagnetic forces, gravitational forces, strong nuclear force is the strongest force. And guys, it has to be stronger than electromagnetic because it is holding protons together. So you can see this image, it is holding like a rubber band. It is holding like a rubber band the entire integrity of the nucleus. So otherwise protons would rip apart, right? Protons will run away. So that means it has to be stronger than the electromagnetic force. It is stronger than gravitational force. It is the strongest force in nature. Got it, all of you? And just to give you a small glimpse that how strong this force is, just to give you a small glimpse that how strong this force is, I want you guys to pay 100% attention here, okay? You know how strong this force is can easily be understood by the simple understanding of nuclear energy. We all know that humans have never made a bomb more lethal than a nuclear bomb. And nuclear bomb releases such a massive intensity of energy, it releases such high amount of energy that it is very difficult to control, very difficult to contain, right? You know, this energy that comes out in the nuclear explosion is a part of the strong nuclear force. It is simply a small part of the strong nuclear force. It is not the entire energy of the nucleus that is released. It is just a part of the energy that is released. And I'll share a very interesting concept with all of you. It will help you to, find the subject somewhat more interesting. You know, when it comes to measuring the intensity of a nuclear bomb, if you want to check the intensity of a nuclear bomb, we use a concept called as kilotons. Kilotons. What is the meaning of kilotons? Please pay attention. Suppose I have a nuclear bomb of 1 kiloton. Suppose I have a nuclear bomb of 1 kt, 1 kiloton, and this 1 kiloton nuclear bomb is exploded. Suppose this nuclear bomb of 1 kiloton explodes. How much is the energy that will be released in this? 1 kiloton basically means that if this bomb explodes, it will be equal to 1 kilo. Kilo means 1000. So it will be equal to 1000 tons. I hope all of you know 1 ton is also equal to 1000 kgs. So 1 into 1000 into 1000 kilograms equivalents of TNT. TNT is a conventional explosive called as trinitrotoluene. It was an explosive that became very popular in the 19th century, right? Although it was used till the, even it is still used, but it was used till the Second World War. But 19th century, it was a popular explosive at that time. So 1 kiloton basically means that, look at this guys, look at this. 1 kiloton means that if you take 1000 into 1000 kgs of TNT, that means 10 to the power 6, 1 million kilograms of TNT. If you take 1 million kilograms of TNT and burn all this, explode all this 1 million kilograms of TNT in one instance, then the energy that is released, it is going to be equal to 1 kt. Then energy that will be released will be equal to 1 kt. Right? So it is 1 million tons of TNT is equal to 1 kt. Got it, all of you? It's called 1 kt, kiloton. There is also another unit for measuring the intensity of nuclear weapons. We call it megatons. Megaton is 1000 kilotons. 1000 kilotons makes 1 megaton. Right? Makes 1 megaton. So it is 1000 times higher than kilotons, megatons. So we can use megatons or we can use kilotons to measure intensity of a nuclear bomb. And now guys, let me share a fact with you. Like I said that it is the strongest force in nature. You will be surprised to know that when the last nuclear test was conducted by Russia, when the Russians conducted their last nuclear test, do you know they released energy up to 3400 kilotons. They released energy up to 3400 kilotons. 3400 kilotons of energy was released when Russians conducted their last nuclear test. 3400. Right? Not, this is 1 million kg of TNT is 1 kiloton. If 1 million into 3400 is burnt in one single go, that is the energy released in just a nuclear test by Russia. When Americans conducted their last nuclear test, they produced 2600 kt. When Chinese conducted their last nuclear test, they produced 2100 kt. And guys, can you tell me, when did India conducted their first nuclear test? When did we conduct our first nuclear test, guys? Anyone? First nuclear test. No, no. 1998 was the time when India became a nuclear weapon state. That was the second nuclear test. The first nuclear test was done, yes, it was Operation Smiling Buddha. Buddha Jayanti was being organized or was being celebrated on that day. It was 1974. Very good, Bharat. Very good. 1974. So we have 1974. We conducted our first nuclear test. And can you tell me which place? What is the name of the site that India eventually called it as the nuclear testing site of India? Where do we have the nuclear? Yes, it is in Pokhran, Rajasthan. Pokhran, Rajasthan. Pokhran is in Jaisalmer district of Rajasthan, right? So in 1974, India conducted its first nuclear test. And do you know how much energy we released in the first nuclear test? We released 8 kT. We released 8 kT. Now guys, you may be wondering that when Russians did it, they produced 3400 kT. When Americans did it, they produced 2600 kT. When Chinese did it, they produced 2100 kT. Indians produced just 8 kT. You may be wondering that whether we really did a nuclear test or not. No guys, understand this. See, 8 kT is also a huge amount of energy. Let me just tell you that the bomb that was used on Hiroshima and Nagasaki, the bomb that was dropped on Hiroshima and Nagasaki, it was having an intensity of nearly 17 kT. It was just a 17 kT bomb. And you all know that it destroyed the entire city. Just 17 kT. So you can just imagine 3400 kT is 200 times more lethal than Hiroshima and Nagasaki. 200 times. And guys, what India did, 8 kT, it is just half of the energy produced at Hiroshima and Nagasaki. But there is a reason why we did a smaller explosion. The reason is, see, when Russians did it, when Americans did it, or when the Chinese did it, when they did the nuclear test, they were doing it to create an international current or international news. They wanted to create sensation that now Chinese are also capable, Russians are also capable, Americans are also capable. Basically, their intent was to show their enemies that we are ready to attack. But guys, when Indians did it in 1974, we did it in secrecy, first of all, right? We did not want to raise an alarm globally. We did not want it to disturb any geographical or geopolitical peace of the world. So we did it secretively. And secondly, when these countries did it, they did an explosion. And when we did it, we did an implosion. Implosion means we did an underground test. So underground test is considered to be the safest test, and the underground implosions cannot go beyond a certain limit. Otherwise, it can cause earthquakes that can be very devastating. So we did an implosion. So our test was an underground test. And guys, let me tell you, in 1961, there was a treaty that was signed called Partial Nuclear Test Ban Treaty. And this 1961 treaty, these are the kind of things that you should keep writing on your own. Okay, don't worry for the teacher to dictate these things. So in 1961, we had the Partial Nuclear Test Ban Treaty signed, and this treaty had actually imposed a partial banning on nuclear tests to be conducted in air, water, or on surface, right? So you cannot conduct a nuclear test after 1961 in air, like atmospheric test was not allowed. You could not conduct a nuclear test in water, oceanic tests were also not allowed, and you could not conduct a nuclear test on the surface. So there was only one place where you could conduct the nuclear test after 1961, and that was subsurface, inside the surface. And that's what India respected. Even though India never signed the treaty, India never signed the 1961 Partial Nuclear Test Ban Treaty, but India still respected the international regime, and we conducted an implosion. And that's why we produced less energy in our nuclear test. Are you guys able to understand? Tell me yes in the chat quickly. Are you able to understand the meaning of KT? So this energy that comes out in the form of tons of TNT, this actually is a small part of strong nuclear force. That's how strong the strong nuclear force is. And guys, just to give you a quick example, look at this. If you just forget this particular word right now. So if you take 1 kilogram of uranium or plutonium, it will produce 17.5 kilotons of TNT. That means the bombs that were dropped on Hiroshima and Nagasaki were typically a 17 kiloton bomb, right? A 1 kilogram bomb. It was just having 1 kg of uranium or 1 kg of plutonium, and that's it. Are you guys able to get it? This is what we have under strong nuclear force. It is the strongest force in nature. Strong nuclear force. I hope all of you guys are able to understand. Strongest force in nature. Strong nuclear force. Now look at this. Guys, now we have the two other forces, and if you remember, we have left space for the fourth statement. We have left space for the fourth statement in gravitational force and electromagnetic force. Under gravitational force, please write down the fourth statement now. I hope you guys have left space for the fourth point. Under gravitational force, please write down the fourth statement. Write down gravitational force. The fourth statement is, please write down, it is the weakest force in nature. So out of these four forces, gravitational force, electromagnetic force, strong nuclear, weak nuclear forces, the weakest out of all these four forces is gravitational force. The weakest of the force is gravitational force. Gravitational force is the weakest force. Got it? And guys, under electromagnetic force, write down the fourth point. Electromagnetic force, it is the second strongest force in nature. So after strong nuclear force, the second strongest force in nature is electromagnetic force. Electromagnetic force is the second strongest force in nature, and I hope all of you guys are able to understand. So these are the forces: gravitational, electromagnetic, and strong nuclear force. Now guys, I hope all of you have understood strong nuclear force, and now talk about weak nuclear force. Write down quickly weak nuclear force. So what is this weak nuclear force? So this is the fourth force of nature. This is the fourth force of nature, weak nuclear force. And let's talk about weak nuclear force here. So guys, before I talk about this weak nuclear force, there is a term that you guys can see written here called isotopes. You guys can see the term here. It says isotopes. Now what is the meaning of the word isotope? So isotope is a very commonly used word in chemistry. It means those elements. Isotopes, you can write it down if you do not know this. Those elements, in fact, mind my words guys, whatever you find new or whatever you think that you do not know, you can write them down, right? I take enough pauses in between. I go slow. I go in such a speed that students can easily write down the content, right? Because sometime when I'm explaining the things, you guys can use that time to write, right? And also listen. So what is an isotope? Isotopes are basically those elements. They are those elements which have got same atomic number. Those elements which have got same atomic number but different mass numbers. Guys, what do you understand by this? I said those elements which have got same atomic number but different mass numbers, we call them isotopes. Elements which have got same atomic number but different mass number, it's called isotopes. That means their number of protons are same. When I say they have same atomic number, that means they have same number of protons. Their number of protons are same. But guys, when I say different mass number, what will that mean? It has different number of neutrons, because mass number is protons and neutrons. Mass number is protons plus neutrons, right? So they have different number of neutrons. Their number of neutrons are different, right? So they are typically, or they are technically same element. They are technically same element but having a different number of neutrons. Number of protons remain the same. So guys, this is what we have under isotopes. Let us start and understand isotope with some examples. So guys, all of us know when I write hydrogen, all of us know hydrogen is this element 1 atomic number, 1 mass number. All of you would agree? All of you would agree that hydrogen is this 1 atomic number, 1 mass number. This is hydrogen, and all of you would accept that yes, this is hydrogen, 1 atomic number, 1 mass number, right? Hydrogen, one atomic number, one mass number. But now, when I talk about water, the water that we drink, 70% of the human body is water, right? Water is a part of our, drink. We drink water all the time. So when you talk about water, what is this water made up of? Water is made up of 2 hydrogen atoms and 1 oxygen atom, right? Water is made up of 2 hydrogen, 1 oxygen. And if I ask you, what is this hydrogen? What type of hydrogen is this? So this hydrogen is the same, this H1 mass number, H1 atomic number. So H1 is basically the hydrogen that we have in our water. It is the hydrogen that is found in the form of water. It is the hydrogen that is found in our body as well. Got it, all of you? Right? This is the hydrogen, atomic number 1, mass number 1. So guys, it's very obvious. It is very obvious that when the subject of science would have originated, initially, scientists would have started observing all the elements around their vicinity only, right? They would have studied wood, they would have studied air, they would have studied insects, they would have studied different animals, they would have studied animal fur, they would have studied soil, everything that is there around them. जो भी चीज़ें आसपास हैं, they would have picked up those things and they would have studied them. So of course it is obvious that scientists would have picked up water also and would have found that water is made up of hydrogen and oxygen, where hydrogen has 1 atomic number, 1 mass number, right? This is what scientists must have concluded when they would have studied water, right? But now guys, as the scientific temper matured and we somehow started taking samples of difficult locations, like scientists went into the volcanic tubes and took the water samples of the volcanic tubes, groundwater samples. Scientists would have gone to the deepest point in the ocean and took water samples from the ocean surface. Scientists have gone even on moon and they are studying water, the possibility of water on the moon soil. So what is happening, that scientists are trying to, when they go to difficult locations and we pick up samples from there, they studied those samples also, and they discovered that the water that we have available on the surface of the earth, the water that we have available in our body, is actually different than the water which is found at the bottom of the earth, the water that is found at the bottom of the oceans. The water sample that they collected from the ocean bed, they discovered that in those water samples, it was H2O, it was again H2O, but the hydrogen that they had, the hydrogen that was present at the bottom of the ocean, it was having 1 atomic number, but the mass number was 2. That means this hydrogen, which was collected from the samples of the bottom of the ocean bed, it had 1 proton and 1 neutron. And guys, when the scientists found 2 different isotopes of hydrogen, now you can see there are 2 different isotopes, same atomic number, different mass number. There are 2 different isotopes, and when scientists discovered these 2 different isotopes, they started naming them. They started giving a name to them. And guys, the easiest name, the first name that was clicked was that this hydrogen became light hydrogen because it has just 1 particle in its nucleus, and this hydrogen became heavy hydrogen because it is having 2 particles in its nucleus. This became heavy hydrogen, right? So this H2 became heavier version of hydrogen, H1 became lighter version of hydrogen. And guys, then water, the water that contains light hydrogen, it should ideally be called light water. So the water that we drink, the water that we have in our body, is typically light water. And similarly, any water that contains heavy hydrogen, it will be called heavy water. Any water containing heavy hydrogen, it will be called heavy water. So did you guys understand how light water, heavy water came into existence? Light water is the hydrogen that we drink. So this water likely is light water. The hydrogen that we are drinking is light water, and the hydrogen that is made from heavy, the water that is made from heavier isotope of hydrogen, it is called heavy water. Got it? And guys, this is how the 2 isotopes of hydrogen were discovered. But guys, the story doesn't end here. Then what happened? Scientists took samples from the moon soil and when they studied the soil of moon, they discovered that on the moon soil there is another isotope of hydrogen existing, and they found out that this hydrogen is having the same atomic number 1, but the mass number is 3. Having the same atomic number 1, but the mass number is 3, H3. So H1 light hydrogen, H2 heavy hydrogen, but now there is a heavier version of heavier version here, H3. And guys, when scientists discovered this H3, a new isotope, from where did they discover this? From the samples collected from moon. So various moon missions have collected the sample from moon and brought them back to earth, and scientists discovered this H3 in those samples. And now the question that you should ask, what do we call this H3? Because this is heavier than the heavy hydrogen. But guys, the word heavy is already taken. So how do you name this H3? What name did the scientists give to this H3? So guys, scientists, when they studied H3, they discovered this H3 has a unique property, and that property was radioactive. This H3 was a radioactive isotope of hydrogen. And now what you should ask, what is radioactivity? Right? You should ask what is radioactivity. So this third version of this third isotope of hydrogen, H3, it was discovered from the soil samples of moon, and this hydrogen happens to be radioactive in nature. So now guys, the question is, what is radioactivity? Can anyone answer? What is radioactivity? Can you guys try and answer? What is radioactive? What is the meaning of the word radioactive? Right? What is the meaning of the word radioactive? Can anyone try and answer? Radioactive का मतलब क्या होता है? Alright, so see guys, radioactivity, if I would define radioactivity in a simple way, I would simply say radioactivity is manifestation, or you can say it is when a nucleus is unstable. Acha chalo, let's forget this point for a while. Guys, yes, it is called nuclear decay. Very good. Radioactivity is called nuclear decay when an unstable nucleus tries to attain stability. Okay, good. But let me put it in a different way, right? Guys, have you heard of this film Interstellar? Have you heard of this movie Interstellar? How many of you have heard of it? Interstellar? Yes, Harry, very good. Alpha, beta, gamma. Okay, Sagar has heard of it. Ivani have heard of it. Nihal have heard of it. Okay, just few students have heard of the movie Interstellar. And I believe you guys have even watched it. How many of you have watched the movie Interstellar? Okay, Vani, you have watched Interstellar. Alright. Alright. Nihal, I believe you have also watched. And Sagar, I believe you also watched. Now, you know, how did you like the film? What do you guys think? Did you like the film? Was the film good? I'm not asking any one of you to watch the movie. I'm not promoting the film here. Actually, the film is the reason why I'm asking this, because the film itself has been made on a very interesting idea. The film is made on an idea that planet Earth is about to die. So NASA sends some expeditions of astronauts to different possible planets where humans can be sent to settle. So it was basically a movie in order to resettle humans to different planets. That's basically the entire context of the film. But why have I asked you about this film? I'm not asking you to watch. If none of you have watched the film, there's no problem. You don't have to watch the film to understand this conversation. But the reason why this film is popular is because how accurately it has depicted everything. It has tried to show almost every space phenomena, almost every, if in reality these things would occur, they have tried to show it in the most accurate manner, right? Theoretically accurate manner. Now, the reason why I asked you this, you know, the movie Interstellar, the scientific advisor, the person who gave all the scientific theories, the person who was sitting with the writer of the film to make things scientifically correct, his name is Dr. Kip S. Thorne. Dr. Kip S. Thorne. Dr. Kip S. Thorne is a Nobel laureate, right? Dr. Kip S. Thorne is a Nobel laureate, and Dr. Kip S. Thorne, he was the scientific advisor of the film Interstellar. Now, guys, you have heard of Dr. Stephen Hawking? You have heard of him? Dr. Stephen Hawking died in March 2018. In March 2018, Dr. Stephen Hawking died. I remember in September 2018, his last book was published. His book that he completed before his death, it went into printing, publication, designing and all those things, editing and everything. And this is his last book got published in September 2018. The name of the book is Brief Answers to Big Questions. So there were almost 10-15 important questions that have not been answered yet, and Dr. Stephen Hawking is trying to give his explanation in answering those questions. Now the foreword of the book, Brief Answers to Big Question, is written by Dr. Kip S. Thorne, right? So कितने references दे दी मैंने आपको. Dr. Kip S. Thorne has written the foreword of the book, Brief Answers to Big Questions. Now guys, Dr. Kip S. Thorne says, or he writes in the foreword, a statement which is very simple, but I often use this statement in the class because it's a very powerful statement in terms of understanding nature, in terms of understanding science. Dr. Kip S. Thorne says, nature has a natural tendency of absorbing any kind of instability. If you want, you can use this statement. It has been officially written by him. Nature has a natural tendency of absorbing any kind of instability. So you create an instability, nature will find a way to absorb it somehow. Like guys, when the COVID pandemic came, suddenly people did not have immunity against the COVID pandemic. But did you guys heard about this concept called herd immunity? Have you heard of this concept called herd immunity? Like many countries did not lock down, many countries did not go into lockdown, stating that slowly this virus will spread among people and slowly people will develop immunity and all the people essentially will become immune. Like guys, when it comes to India also, actually India needed to lock down the entire country because we were having a high population. But small countries need not have to apply any lockdown because they thought that if 1% people also get affected, that will not be a concern because 99% of people do not even get affected. They remain asymptomatic, right? That was the news that we were hearing initially. So UK took this particular risk and they did not call for a lockdown. I remember the Prime Minister of UK that time, some Johnson, right? So who looked very similar to, yes, Boris Johnson. Yes, thank you, Srinath. Boris Johnson. So Mr. Boris Johnson was the Prime Minister, and you may be knowing that UK delayed the lockdown for almost 15 days, considering that this virus will slowly start spreading. Less than 1% people will show symptoms, and out of those 1%, only nearly 1% people will be at risk. So we'll easily hospitalize those 1% people, and rest of the people will slowly develop herd immunity. So herd immunity is basically nature's response. It is a natural phenomenon, guys. It is nature's response of adapting against a viral strain or a disease. You guys may have heard that these kind of events have happened previously also, right? These kind of events have happened in 1920 Spanish flu. A lot of people died, but you can understand nature has its own way that less than 1 or 2% people gets infected seriously and rest of the people simply develop herd immunity, right? This is nature's response of stabilizing whenever any instability is creating. Now guys, I'll give you some more examples. Do you guys know dinosaurs? All of you know dinosaurs, right? So all of you know that dinosaurs got extinct 65 million years ago. Do you know how did the dinosaurs die? A college student may be able to recall. How did the dinosaurs really went extinct? How did the dinosaurs die, guys? Dinosaurs died because of an asteroid collision. There was an asteroid from space that had hit Earth, and but there was a series of asteroids basically that had hit Earth, and this collision was so strong that it it is believed that this collision would have produced energy equivalent to 8,000 to 10,000 nuclear bombs. Energy equivalent to 8,000 to 10,000 nuclear bombs was created in that explosion, and that collision was so massive that it created massive levels of volcanic eruptions. It released so much of dust that the entire planet Earth got encapsulated in dust. Entire planet Earth got covered with dust. And when the entire planet Earth got covered with dust, sunlight could not pass, and the temperature of Earth dropped. The temperature of Earth dropped, sunlight could not pass. And guys, what kind of animals were dinosaurs? Dinosaurs were cold-blooded animals. We have talked about cold-blooded animals in ecology as well. Even in biology, we'll talk about them. Cold-blooded animals. What is a cold-blooded animal? A cold-blooded animal is one whose body temperature depends on the surrounding conditions. You must have seen lizards, house lizards. Today in this season you can see house lizards inside the house, because the summer season is somewhere the house lizards are able to manage their temperature, because if the summers are there, house lizards find this temperature conducive. But in the winters, house lizards are nowhere to be seen. They hibernate because they know winters are harsh for their survival, so they eat a lot of food and go into a deep sleep, winter sleep, hibernation. All of you understand? So cold-blooded animals are those reptiles, amphibians and fishes. All three of them are cold-blooded, and these animals are those which cannot maintain their body temperature, which cannot maintain a constant body temperature. They are always dependent on the outside temperature for their survival. So you guys know that snakes, they always are found along those places where they are cooler, right? Because otherwise in the daytime they can't survive the harsh sunlight, right? So these are called cold-blooded animals. Reptiles, birds, reptiles, amphibians and fishes, cold-blooded. So guys, dinosaurs were also reptiles. And when the entire planet Earth got covered with dust, the temperature started dropping. Many dinosaurs would have tried to migrate, but they did not find any suitable place to go. Many of them would have tried to go into hibernation, thinking that this dust will settle, but they did not. Went to hibernation also, could not recover. And many of them would have tried to, somewhat adapt, but none of these things happened, and the dinosaurs got extinct. But guys, think about it. Which animal would have survived this? Warm-blooded. The animals which are warm-blooded are those animals which can manipulate, which can manage a constant body temperature irrespective of the outside temperature. Like right now, if the outside temperature, let's suppose, is 20 degrees Celsius, my body temperature, if I put a thermometer, it will still show 37 degrees Celsius. If the outside temperature is 40 degrees Celsius, my body temperature will still show 37 degrees Celsius. This is how the body maintains its constant temperature. And guys, mammals and birds are warm-blooded animals. So guys, what is interesting in this story is, when the asteroid attack happened, the dinosaurs got extinct. The planet Earth lost nearly 75% of all its species. But do you know, nature eventually absorbed even this instability as well and created a new species. And guys, you can Google it. You will find out that birds and mammals originated only after the extinction of dinosaurs. That means nature understood that the next animal that can survive has to be a warm-blooded animal. So the warm-blooded animals were able to survive, and they are still surviving. Are you able to understand? Nature has a natural ability of absorbing any kind of instability. Got it? So although guys, let me tell you, it's not like mammals originated only after dinosaurs. We had mammalian ancestors even 200 million years back, but they were in the form of primitive rodents. वो primitive rodents के form में थे. Today we see such complications in mammals. It's all after the extinction of dinosaurs, because that was a time when mammals were able to multiply and grow. Are you guys able to understand? Tell me yes in the chat. So nature has its own way of absorbing any kind of instability. So nature absorbed the instability created by the asteroid collision in the form of mammals and birds. And similarly, nature has this idea of herd immunity where if a pandemic occurs, majority of humans will be able to adapt against it and develop a herd immunity, right? Less than 1%, 2% people will likely get affected. I hope all of you guys are able to understand. This is the concept of, this is what Dr. Kip S. Thorne have said. Now, what is radioactivity, guys? So guys, radioactivity is also nothing but an instability, just like we saw instability previously. What is radioactivity? Radioactivity, you can just write down, it refers to instability of the nucleus. It refers to instability of the nucleus. Radioactivity simply refers to instability of the nucleus. And guys, what did I say? Nature has a natural ability of absorbing the instability. So there has to be a way of managing this instability also. So guys, sometimes the nucleus becomes highly unstable. Don't worry, I'll tell you the reason. Right? So when a nucleus becomes unstable, what does Kip S. Thorne says? That nature will find a way to absorb those instabilities. So how is that instability managed when the nucleus becomes unstable? It is managed by releasing that instability outwards. So nucleus, when it becomes unstable, it releases those instability out in the form of radiations. In the form of radiations known as alpha, beta, gamma. Alpha, beta, gamma, these are the radiations that are released whenever you have any unstable nucleus. Alpha, beta, gamma. Don't emphasize on alpha, beta, gamma right now. We'll talk about them later. But first, please write down what is radioactivity. Please write down radioactivity. Write down, guys. Radioactivity, please write down. Write down. Radioactivity refers to instability of a nucleus. Radioactivity refers to the instability of the nucleus. That occurs due to imbalances of charges within the nucleus. Guys, just write this definition right now. Do not ask me to explain this definition. I can explain radioactivity in depth also, but you will have to wait. There is a topic called standard atomic model that I'm going to discuss with you. There I'm going to talk about it. So please write down radioactivity. Write down, guys. Radioactivity refers to the instability of the nucleus. That is due to the imbalances of charges within the nucleus. Right? That is due to the imbalances of charges within the nucleus. Full stop. The nucleus tends to release this instability. The nucleus tends to release this instability in the form of radioactive radiations. Such as alpha, beta, gamma plus heat. And heat. So whatever instability is there inside the nucleus, this instability is released out in the form of alpha, beta, gamma. Very good, Harry, you have written very nicely, that those are highly unstable nucleus goes under continuous disintegration in terms of discrete energy, in terms of alpha, beta, gamma rays. Very good, very nicely written. But I hope you all are able to understand the definition which I have also given. It is basically, so radioactivity is basically a phenomena which is manifested by an unstable nucleus, and instability of the nucleus occurs due to imbalances of charges inside the nucleus. If you want, you can write down this particular part, imbalance of charge within the nucleus, because you can ask this question that how the nuclear charges are imbalanced. So I will explain this part when I discuss standard atomic model. So imbalance of charges within the nucleus, and this radioactivity is managed by the release of alpha, beta, gamma rays plus heat. Right? I hope all of you guys are able to get it. This is what we have under radioactivity. And remember, guys, this radioactivity is a phenomena that is manifested by an unstable nucleus. So when an unstable nucleus becomes stable, so in order to become stable, radioactivity is so you can write down this point. Acha, you guys tell me, will radioactivity be a permanent phenomena or an temporary phenomena? Remember, radioactivity is manifested till the time the nucleus is unstable, and it was manifested in the form of alpha, beta, gamma and heat. So if a nucleus have released enough alpha, beta, gamma and heat that now all the instability is gone, don't you think it should become non-radioactive later on? Sagar, what do you think? It should become non-radioactive later on. So radioactivity is a temporary phenomena. Remember that. Please write down. Radioactivity is a temporary phenomena. Radioactivity is a temporary phenomena. It exists only. Radioactivity is a temporary phenomena. It exists only till the time a nucleus is unstable. Right? It exists only till the time the nucleus is unstable. It exists till the time the nucleus is unstable. Okay? The nucleus is unstable. Remember that? And you can also write down this expression: radioactivity is a phenomena through which a nucleus attains stability. So radioactivity is a phenomena through which a nucleus is attaining stability. An unstable nucleus is attaining stability. Okay? So radioactivity is a phenomena through which an unstable nucleus is trying to achieve stability. Got it? And this is a temporary phenomena. Remember that radioactivity is a temporary phenomena. Remember this. Got it? So radioactivity is a temporary phenomena, and this is manifested by this H3. So H3 happens to be a radioactive nucleus. So H3 is a radioactive nucleus. I believe all of you guys are able to get it. H1, H2, H3. These are radioactive nuclei. Now my question to you is, please pay attention. So guys, H3 is a radioactive nucleus. So H3 will emit alpha, beta, gamma as well as heat until it becomes stable. Got it, all of you? Acha, now let me give you the real names of these hydrogen isotopes. Right, so far we call this light, heavy and radioactive, but guys, these three isotopes also have their actual names. इनके अपने खुद के नाम भी हैं. The excuse me, the light hydrogen, its actual name is protium. Light hydrogen's actual name is protium. Okay, the actual name for light hydrogen is protium. Heavy hydrogen, its actual name is deuterium. And radioactive hydrogen's actual name is tritium or tritium. Right? These are the three isotopes of hydrogen: protium, deuterium and tritium. Out of these three, tritium is radioactive, and protium is the lightest, deuterium is heavier, and tritium is radioactive. I hope all of you guys are able to understand, right? This is what we have under the identification or classification of hydrogen isotopes. I hope all of you got it, right? But guys, we haven't understood radioactivity completely. So let's try to understand this concept radioactivity slightly more. So guys, what have we known about radioactivity? That radioactivity is a phenomena through which an unstable nucleus attains stability. That's point number one. How does it attain stability? By the release of radiations like alpha, beta, gamma and heat. And we also have learned radioactivity is a temporary phenomena. That means till the time a nucleus is unstable, it will emit alpha, beta, gamma plus heat, and slowly it will disintegrate enough that it will attain stability. I hope all of you understand this. So radioactivity is a phenomena through which it attains stability, unstable nucleus. How does it attain? By release of alpha, beta, gamma and heat. And third is, it is a temporary phenomena. Right? Please write down yes in the chat if all of you are able to agree. All of you are able to agree to this. Please write down yes in the chat, guys, quickly. All right, perfect. So this is what we have under radioactivity. These are the three things that we have understood about radioactivity, right? Perfect. Now my point is, what about these alpha, beta, gamma rays? ये होती क्या है? How are these alpha, beta, gamma rays important, and what is their nature? So guys, I have still not talked about alpha, beta, gamma. I am yet to talk about that. So if you may allow me to talk about alpha, beta, gamma, see what happens. The alpha rays, you can write down these points here. The alpha rays, because I have not discussed helium, ion and such things, I have not talked about any of these things. So I'm giving you very basic minimal information, right? alpha rays are actually positively charged rays. You can write down alpha rays are, or alpha particles are positively charged particles. And guys, these alpha particles, they have low penetration power. Their penetration power is less, but they have high ionization power. They have low penetration power, but they have high ionization power. Their ionization power is high. What is the meaning? Don't worry, I'll explain this. So they have high power of ionization but low power to penetrate, right? And third point, write down. So guys, imagine if there is a radioactive substance right in front of me and it is throwing alpha particles towards me. Alpha particles, I can easily protect myself. I can easily protect myself by simply putting a sheet of paper in front. If I put a sheet of paper in front of the alpha particle, because alpha particle has poor penetration power, it cannot penetrate beyond a sheet of paper. It cannot penetrate beyond a sheet of paper, and I would be protected against the alpha particle. Got it? Alpha particle can easily be prevented with a sheet of paper also. Got it? It has less penetration power. But guys, did you say it says it has got high ionization power? High ionization power matlab kya hota hai? What is the meaning of high ionization? So guys, what it means that when these particles, when these alpha particles are going to touch any surface, it will break down the atoms into its ionic form. So ions are basically nothing but, see, just now what did I tell you guys? Shortly, atoms, they are electrically neutral, right? Didn't I say this? Atoms are electrically neutral. I want Shritama and particularly Sagar and Shritama to answer this. Atoms are electrically neutral. Why they were electrically neutral? Because number of electrons were equal to number of protons. Remember? Tell me, both of you, Shritama and Sagar. Atoms are electrically neutral because electrons and protons are equal. But guys, there is another type of atom called ions. What is an ion? Ions are called charged atoms. Ions are called charged atoms. And what are these charged atoms? Charged atoms are basically those where the number of electrons and the number of protons are unequal. That means there is some kind of distortion, there is some kind of difference in the number of electrons and protons. And when there is some kind of difference in number of electrons and protons, whatever is the net charge, let's say for example, if there are 10 protons, right, and 9 electrons, so there would be 1 positive net charge. The net charge is 1 positive. If there are 11 electrons and 10 protons, वैसे possible नहीं है, 9 protons and 10 electrons, then there would be net negative charge, right? What I'm saying is ions are actually called charged atoms. And how are these atoms going to get charged? It is mostly because of elimination of electrons or absorption of electrons. So normally every atom is going to have same number of electrons and protons. Normally every atom has got same number of electrons and protons. But if there is any electron that is absorbed by the atom, if there is electron from external source gets absorbed into the atom, the number of electron may increase. The atom will develop a charge. It will become a negatively charged ion. But if the electron is lost from an atom, the number of electron will decrease. Number of protons are already high. Number of protons are already same. The atom will become positively charged. Are you guys able to understand? Tell me, Shritama and Sagar, because this is something which is very basic part of science. I don't want to get into the depth of it because ionization will come up later also. So guys, what I'm saying is, perfect guys, if you have understood. So what I'm saying is that let's suppose there was an alpha particle traveling towards me. I was protecting myself with a sheet of paper, right? Because a sheet of paper is enough to protect the alpha particle because it has less penetration power. But somehow the sheet is dropped. Somehow the sheet is gone. Now the alpha particle will be touching my skin. The moment it will touch the skin, it will not penetrate deep into the skin because it has poor penetration. But the moment it will touch the skin, it will cause a quick reaction with all the atoms on the surface and the skin will start burning. the skin will start burning. Nothing will happen internally. No internal injuries will happen, but the surface will start burning. Are you guys able to understand? So this is alpha particles. So alpha particles have less penetration power, but have very high ionization power. Are you guys able to understand? They have high ionization power. Got it, all of you? So guys, what happens? You must have heard, Russians, they have a very unique way of killing their enemies. शायद आपने सुना होगा कभी that Russians, whenever they find out that there is a spy in Russia, they don't capture the spy. They just go and put polonium in his food. Polonium is a radioactive element. They put polonium in his water, or they simply expose the person with some radioactive isotope. What happens? Till the time alpha particle is outside, it can only cause burns on the skin. The skin burns can be recovered in hardly 15 days. But if you have accidentally consumed a radioactive particle, if a radioactive particle has gone inside your mouth, in your stomach, now the alpha particle can cause internal damage of the organs. And just imagine, just like how your skin cells were burning, now your internal organ cells will start burning away. Are you guys able to understand? So guys, alpha particle is very dangerous if it goes inside the body. Are you able to understand? Tell me yes in the chat, all of you. All of you, tell me yes in the chat. This is the basic nature of alpha particles. Only Srinath has been able to understand. Himanshu, very good. Srinath, what about others? Did you guys understand? Alpha particle has less penetration power but very high, very strong ionization power. Got it? Alright, perfect. Now guys, next is beta particle. So what have you written about alpha particle? It is positively charged. It has low penetration but high ionization. If you want, you can write down that it can break atoms into its ions easily. That is the meaning of ionization power. So for ionization power, you can write down it can break atom into its ions easily, or it can convert atom into its ions easily. That is what basically ionization power means. Got it, all of you? Ionization power, right? Okay, I'll define ionization one more time. Okay, just one second. So what was ionization, Vani? I'll repeat this. Ionization simply means a conversion of an electrically neutral atom into its ionic form, into ions, right? So ions basically means when an atom converts into a charged, when an atom which is ideally electronically neutral becomes charged, we call it ions. And how are these ions created? The ions are usually created when there is a difference in the number of protons and electrons. Now protons are there inside the nucleus, their number doesn't change. Electrons which are revolving around the nucleus, their number changes. So if the atom happens to absorb an external electron, the number of electron increases, the atom gains a negative charge because now there are more electrons than protons. If an atom loses an electron, the number of electron decreases, then the number of protons, the atom gains a positive charge, making a positive ion. That's basically the idea. Are you able to understand, Vani? Alright, even if you have a problem here, don't worry guys. Ionization, I will be discussing it. It will be an important part of discussion when I discuss energy technology, right? Because to understand batteries, it is important to understand, appreciate ions clearly. Okay, so coming back to this, they have high ionization power. So you can just write down that they have a strong tendency of breaking atom to its ions. That's what is the meaning of ionization, right? Strong tendency of breaking atom into its ions. Now guys, the second particle is beta particle. Now what do we know about the beta particle? Beta particle happens to be negatively charged. Beta particle is a negatively charged particle. It's a negatively charged particle, and these particles, beta particle, this particle has higher penetration power than alpha and lower ionization power than alpha. So in terms of penetration, so guys, if I put a sheet of paper, suppose there is a beta particle traveling, I put a sheet of paper, a beta particle can easily pass through a sheet of paper because it has higher penetration power. So a sheet of paper may not be enough. A sheet of paper may not be enough to prevent the entry of beta particle. But guys, I don't have an aluminum foil here, but I think I have some wrapping paper. Yes, let me use this wrapping paper. So let's imagine this is an aluminum foil, right? So A sheet of paper can easily stop alpha particle, but it cannot stop beta particle. For beta particle, I would need a foil, an aluminum foil. An aluminum foil would be enough to stop a beta particle because its penetration power is stronger. If I don't use aluminum foil also, the beta particle can easily enter deep into the skin. It can enter deep into the skin. Skin, I'm saying, not deep into the body. So it can easily go deep into the skin and cause more severe burns in the internal skin. So it takes almost a month to recover from the burns that are caused due to beta particles. Right? It takes almost a month to recover from the burns of beta particles. Are you guys able to understand? Beta particles. So they have less ionization power than alpha and higher penetration power than alpha, beta particle. And now guys, last is gamma particle. Gamma particles are basically, technically they are not particles, they are radiations, they are neutral. Gamma rays are neutral. They are neutral, they do not have any charge, right? And because of their neutral nature, they have least ionization power. Out of the three, out of alpha, beta, gamma, they have got least ionization power. But guys, gamma rays have highest penetrating power. They have highest penetrating power. They can penetrate deep into your cells, into your nucleus, and can damage your DNA. They can cause, although their ionization power is less, but they can penetrate deep into your nucleus, your cellular nucleus, and damage your DNA, can do ionization of your DNA. And guys, you know what? When the Hiroshima Nagasaki bomb got dropped, there is a very interesting book. It has been written by Matthew Haig. He's an American journalist. The name of the book is Reasons to Survive. The book looks like a book on life course or life coaching, but it is actually nothing but 4 real stories of the people who survived Hiroshima, right? So when the Hiroshima bomb attack happened, these are random stories of 4 people. Although out of these 4 people, one of the person died after 1.5 years due to the radioactive poisoning he developed. 1.5 years the person died, but 3 people survived. It was all because of the locations where they were. Like one of the person was doing fishing, and when the attack happened, his boat got capsized, he got drowned, or he fell into the lake, and water basically prevents the alpha, beta, gamma particles to reach further, and he was somehow protected, saved by the lake, right? So these are stories of 4 people. But guys, the 4 people's story, more than that, the entire situation that has been depicted is horrifying. And in that book, Matt Haig writes a statement which is itself a very painful and a very powerful statement to listen. He says that when the attack happened, the lucky ones died immediately. Think about it. When the nuclear bomb was dropped, the lucky ones died immediately and the unlucky ones survived, right? That means the people who died immediately after the nuclear bomb, they were still the lucky people. And the people who survived the nuclear bomb, they were the unlucky ones, because they did not just have to face the heat of the bomb, but now they have to face the radioactive radiations released from that same bomb. You'll be surprised to know, guys, that the radiation released is so massive that, first of all, let me just depict how the things happened. So the place where this particular bomb was dropped, it was a building with a dome shape. It's called the Hiroshima Dome building. So the place where it was dropped, the people who were in the vicinity of hardly 2 kilometers, the people who were there in the vicinity of the 2 kilometers radius, their whereabouts have never been discovered. The temperature reached up to 9,000 degrees Celsius, and at that temperature, the human body does not even melt, it vaporizes. So you'll be surprised to know that there were thousands of people whose whereabouts have not even been discovered. There are only shadows left. सिर्फ shadows ही बची थी कि यहाँ पे कोई लोग थे. Nothing was left before the shadow because everything got vaporized. The temperature was 9,000 degrees Celsius when the bomb attack happened. And still,
Matt Haig says that these were the lucky ones, because the people who got exposed not just to the heat, they got third degree burns, second degree burns, they got exposed to the radioactive radiations of alpha beta gamma, and their bodies started responding to it in a very unrealistic manner. You guys must have heard there were so many kids who have been born to these people with permanent deformities, permanent disfigured faces and such. You must have heard of the stories, right? You must have seen images of the people who survived the Hiroshima, the kids who were born out of Hiroshima. And guys, mind my words, the young people, kids and mothers, pregnant mothers, they are the most vulnerable to radioactive radiation. You know why? Alpha, beta, gamma. Alpha, beta, you understand, they can only cause burns on your surface. But gamma can penetrate deep into your cells and cause mutations at the deepest level. Now, if there is a person who is an elderly, already has crossed a certain age, this person is less likely to develop any after effects of radiation. Why? Because the cells are not multiplying. And if the cells are not multiplying, there is less chance of DNA damage to occur, because DNA is most vulnerable only when it is multiplying. So DNA mutation can occur only when it is multiplying. When the cells are not multiplying in your body, DNA is closed. Those of you who have a biology background, they may be knowing that it is in the form of chromatins, which is nothing but closed form of DNA, and DNA is completely safe when it is not in the division phase. But when the cells are dividing, that is where the chance of mutation is highest. So guys, you all know, when the mother is carrying a baby in her womb, the baby is multiplying at a very fast rate. The radiations, the gamma rays, can cause very severe permanent damages to the baby. Similarly, when you take young children who are growing at a very high rate, young children are growing up till teenage, people are growing, right? Up till 18 people are growing at least. So till that age, there is a possibility that a person may develop mutations because of gamma rays. It is the cellular multiplication that makes the gamma ray mutation more vulnerable. A person who's old will have less chance. You'll be surprised to know, guys, in Chernobyl nuclear disaster, I hope all of you guys have heard of Chernobyl. It was a place now in Ukraine, and it was the name of a nuclear reactor that was in Soviet Union that time, now in Ukraine. And this nuclear power plant, it exploded, right? Now, when that explosion occurred, the entire city, there was a city called Pripyat, which had almost 35,000 people living. The entire city was evacuated. But you'll be surprised to know 300 old people agreed to stay back. 300 old people, they refused to go because they did not want to leave. They said that they have spent their entire life in taking care of the entire nuclear power plant, so they did not leave at all. They stayed. And it is interesting that none of those 300 people died of cancer. They all died naturally. None of them got affected by the nuclear radiation because the rate of multiplication of the cells is slower in elderlies. Are you guys able to understand? Guys, these are not the things which are given in books. There is no book which has talked about these things. I hope you understand. These are the things which can only be delivered in class. ये सिर्फ क्लास में हो सकता है, ये बुक्स में नहीं मिलेगा आपको, right? These are acute scientific nuances which mostly books do not mention these things. I hope all of you understand. So Matt Haig gave me this insight, and that's what I'm delivering you with the help of some scientific backing. So Matt Haig mentions the stories and he used this expression. I hope you understand how powerful this statement is, right? That the lucky ones died immediately and the unlucky ones survived. So it was the unlucky people who faced all these alpha, beta, gamma and heat and saw so much of damages occurring. I hope all of you guys are able to understand. This is radioactive radiations. Got it, all of you? Tell me yes in the chat if you guys have understood radioactivity. Although I've still not told you the reason behind radioactivity. All right, perfect. So this is what we have under radioactivity. Now it says, so guys, remember, radioactivity is also called nuclear decay because the nucleus is decaying from an unstable nucleus to a stable nucleus. Now guys, my question to you is, we have learned that radioactivity is a temporary phenomena, right? We have learned that radioactivity is a temporary phenomena, and if it is a temporary phenomena, guys, that means tritium, which is radioactive today, once it loses all its instability, once the radioactive tritium loses all its instability, once the instability is gone, don't you think the element should not remain tritium anymore? Once the tritium has lost the instability, do you think it will remain as tritium or should it turn into some other element? Guys, it will transmutate. There is a word that we call as transmutation. In a radioactive substance, when the instability is eliminated, the element also transforms into a stable isotope. So guys, tritium is tritium only till the time it is radioactive. When tritium loses all its radioactivity, when tritium loses all the radioactivity, then you would notice, guys, that tritium will not remain tritium. Tritium will turn into the nearest stable nucleus. So please write down this point. Radioactivity is a temporary phenomena. Radioactivity being a temporary phenomena. Please write down the statement. Radioactivity being a temporary phenomena changes the nature of elements. Changes the nature of elements. Changes the nature of elements. That is, changes the nature of elements. That is, a radioactive nucleus transmutates. You can underline the word transmutate. A radioactive nucleus transmutates, in bracket write down transforms. Transmutates. We use the word transmutation for this. It is just the jargon used in nuclear energy. A radioactive substance transmutates, or in bracket write down transforms, into a stable nucleus. Into a stable nucleus, or you can say a stable element, into a stable element, once it loses all the radioactivity, or once it loses all the instability. So once it loses all the instability, a radioactive substance transmutates into a stable nucleus, right? It transmutates. So guys, my question to you is, if tritium is radioactive, it will remain radioactive until it has all the instability. But what will happen when tritium will lose the instability? As tritium loses its instability, it will not remain tritium any further. It will transform from tritium into the nearest stable nucleus. And guys, this is you guys who are supposed to answer, which is the nearest stable nucleus to tritium. So when the tritium undergoes transmutation and becomes stable, in which elemental form it will convert into? Tell me guys quickly. When the tritium converts into a stable nucleus, in which form it will convert into? Tell me guys quickly, guys, come on. Srinath is saying deuterium. I like your thinking, Srinath, because deuterium seems to be the closest radioactive element to tritium. Guys, for our understanding here, you can consider deuterium. आप consider कर भी सकते हो. But the right answer is what Vani has written. It will convert into helium. It will convert into helium-3, an isotope of helium, helium-3. But don't worry guys about helium-3. I will talk about helium-3 later on when I'll discuss nuclear fusion. Right? जब मैं nuclear fusion बात करूँगा तब बात करेंगे helium-3. Right? So you can here just write down that tritium transmutate into helium-3. See, normally helium has a mass number 4, but this is helium-3. And guys, you can relate this with the news on helium-3 that is coming up, that one of the reasons of going to moon is to find helium-3 reserve. China has already discovered helium-3 on moon. So why helium-3 is important? Because helium-3 is an element that is formed after transmutation of tritium. So when tritium completely loses all its radioactivity, it converts into a helium-3 ion or helium-3 isotope. Got it? Helium-3. Now how it happens, why it happens, don't worry, we will talk about this sometime later. Right? So this is what we have under, because I have not discussed alpha decay, gamma decay, beta decay. I have not discussed these things. Or to be honest, there is no need to discuss alpha decay, beta decay. But if when we study standard atomic model, I may have an opportunity of talking about it. I may talk about it there, right? But otherwise it is not required. So this is something that you can only remember, but when we study those topics in detail, you can ask me, sir, can you relate transmutation with this? So I can talk about alpha decay, beta decay. It's nothing but basic mathematics. Okay, so here just remember that a radioactive substance will convert into its nearest stable nucleus. Where is the nearest stable nucleus? That may not be deuterium. It could be some isotope of helium as well. So this is what we have under the three isotopes and also radioactivity. Now guys, there is a concept given here called half-life. This is the last concept of general science in nuclear energy, and after that we'll talk about nuclear technology, and I'll finish this concept today itself. Even if the class gets extended by 10 minutes, do bear with it. I will finish this concept today. So the topic is half-life. Now what is half-life? It is a very interesting concept, and to talk about half-life, I would first like to give you an example, or first I would like to share one example with you, and that example will be giving us a context to understand half-life better. So guys, all of you are aware about the Harappan civilization, I believe. Even if you have not studied history, but I believe all of you are aware of the Harappan civilization, right? Please write down yes in the chat if you guys are aware of Harappan civilization. As of now, there are a lot of discussions going on Kiladi, right? The excavation that have been found in Kiladi, Tamil Nadu, right? So all of you are aware of Harappan. All right, very good. Guys, in Haryana, there is one Harappan site which is somewhat close to Delhi. If people from Delhi want to go see Harappan sites, they will have to drive for 4 hours and they will reach this particular location in Haryana. The name of this location is called Rakhi Gadi. Rakhi Gadi is a location in Haryana. It is close to Hisar in Haryana, and this particular site is a Harappan site. It is having the actual Harappan colony settlements and such. Now guys, in 2007, while excavations were going on in Harappa, there was a fully preserved skeleton of a woman discovered. There was a fully preserved skeleton of a female that was discovered in the Rakhi Gadi site. Guys, this particular skeleton was then sent to the Pune University. Why Pune University? Actually, Pune University has a very sophisticated archaeological laboratory, right? And this laboratory has been designed and developed in collaboration with the French government. And we know that the French people are very famous in keeping artifacts in the museum and such, right? So although most of these artifacts are nothing but stolen artifacts of Africa, but they have kept it there. So the French government has preserved those things. So they have helped India to set up this particular archaeological laboratory. Now the purpose of sending this particular skeleton to Pune University was that Pune University professors will conduct their research, and they will find out what is the age of this skeleton. Is it of Harappan times or is it later Harappan times? I hope all of you understand. So guys, the Pune University professors, they studied that skeleton. And can anyone tell me what is the name of the technique that we use to find age of archaeological specimens like these? Can anyone answer this? What is the name of the technique that is usually used? It is called carbon dating, or what is famously called as radioactive carbon dating, right? Carbon dating or radioactive dating. This is the technique that we use to identify age of archaeological specimens, right? So guys, like you have written carbon dating, let me quickly talk about carbon as well. So when you talk about carbon, carbon also have got 3 isotopes. There are 3 isotopes of carbon as well. One is C12, mass atomic number is 6 in all of them. Second is C13, and third is C14. Out of these 3, C14 happens to be radioactive. Out of these, C14 happens to be radioactive, right? And guys, we all know radioactivity is a temporary phenomena. C14 also being radioactive will not remain radioactive forever. It will turn into some stable nucleus, right? All of us can easily understand this by default. We understand this. So guys, radioactive carbon dating. So carbon also have got one radioactive isotope called C14. Now guys, let's talk about half-life. What is half-life? I want you to please write down the term half-life. Please write down, guys, what exactly is the meaning of the word half-life? So guys, half-life is actually, so as we know, don't try to understand this. As we know that no substance can remain radioactive forever, that means if no substance can remain radioactive forever, there has to be a certain time period when a substance would disintegrate and become stable. So what is half-life? Half-life, you can write down, it is the time taken by a radioactive nucleus. It is a time taken by a radioactive nucleus to decay. It is a time taken by a radioactive nucleus to decay into its stable form. It's a time taken by a radioactive nucleus to decay into its stable form by half of its by half of its previous size. It is a time taken by a radioactive nucleus to decay by half of its previous size. What does that mean? Please pay attention here. It means that, let's suppose, we all know that tritium is a radioactive nucleus, and guys, there is a formula through which half-life of tritium can be calculated. There is no need to remember the formula. I can tell you the formula, but there is no need to remember because UPSC does not ask numericals. So there is a formula which can help you to calculate the half-life of tritium. And guys, the half-life of tritium has been found out to be 12 years. This is the half-life of tritium. In 12 years, half of the tritium will decay. So what does it mean? What does it mean, guys? Please pay attention. That means if I have this much of tritium with me today, suppose I have got this much of tritium with me today, if I wait for 12 years, then in this time, half of this entire tritium, if I wait for 12 years, then in this time, half of this entire tritium is going to decay in 12 years and convert into a stable helium-3 isotope. Half of the tritium will get decay. Suppose if, and only this much of tritium would be left radioactive. Suppose if I wait for another 12 years, then another 12 years, half of this tritium will decay. Another 12 years, half of this tritium will decay. And this will also convert into helium-3. If I wait for another 12 years, half of this tritium would decay. Another 12 years, half of this tritium would decay. So basically, guys, theoretically, this particular half-life can be broken into infinite cycles. So with every passing half-life period, half of the previous radioactive size gets decayed into a stable nucleus, and only another half remains, right? Only another half remains. So let's suppose if I have got 10 grams of tritium with me today, after 12 years, only 5 grams of tritium would be left. Rest 5 will convert into helium-3, non-radioactive. If I have this 5 grams of tritium with me today, I wait for another 12 years, 2.5 grams will be left. I wait for another 12 years, 1.25 grams. Another 12 years, 0.675 grams. Likewise, it will keep on disintegrating by half of its previous size. And guys, the theory says it will keep on happening till infinity. So there is no such specific time when the half-life cycle would ideally stop. It should keep on happening continuously without any breakage. So it will keep happening like this. So this is called half-life. So half-life is the time taken by a radioactive nucleus to decay by half of its previous size. So guys, tritium's half-life period has already been calculated. Here, let me tell you the half-life period of C14. Carbon 14 has a half-life period of 5,753 years. This is the half-life period of carbon 14, 5,700. For the sake of calculation, let's keep it 5,000 years. Okay? Just for the sake of calculation, let's keep it 5,000 years because we will use this for calculating something, right? So half-life of carbon 14 is 5,000 years. Now the point is, how is this particular carbon 14 dating is used for managing or finding out age of a specimen. So guys, all of you guys know, those of you who have studied ecology, they know something called biomass, right? What is biomass? Biomass is basically dry weight of an organism. Biomass is basically dry weight of an organism. It means weight of an organism minus weight of water. Remember, yesterday also I have talked about this. So it means dry weight of an organism. So let's suppose if my weight is 100 kg, we all know human body 70% is water. So 100 minus 70 is 30. 30 kg would be my biomass. 30 kg is going to be my biomass because that is the dry weight, right? 100 minus 70, 30 kg. Got it? So biomass is dry weight. So let's suppose if there is a person who has a 100 kg weight. In this 100 kg person, 30 kg would be the biomass. Please pay attention, guys. 30 kg is going to be biomass, right? And guys, in this 30 kg biomass, you'll be surprised to know nearly 50% is carbon only. वैसे 49% होता है. It is actually 49%, but for the sake of calculation, nearly 50% of all this biomass is carbon. Nearly 50% of all this biomass is carbon only. 50% of the biomass is carbon, right? That's point number one. And guys, if 50% of the biomass is carbon, then how much is it? It means it is 15 kg. 15 kg is carbon. Got it? And you know what, guys? If I ask you this question, whatever carbon we have in our body, from where we have got this carbon, guys? Tell me quickly. From where we have got the carbon of our body? जो हमारी body में carbon है, whatever carbon we have in our body, from where have we got this carbon? Tell me, guys, quickly. From where we have got this carbon? Anyone? See, we have got this carbon from the food that we eat, right? That is the only source. We intake something, we intake food, so we get this carbon from the food. And how does the food get this carbon? The food that we eat could be meat or plants, but ideally it is plants only because plants are the primary producers. So we get all our food from plants. And how does the plant gets their carbon? They get carbon through photosynthesis, because in photosynthesis they absorb the atmospheric carbon, CO2, sunlight and water from the roots and convert it into biomass. Got it? Tell me yes in the chat quickly. If I ask you from where we get all our carbon, we get the carbon from plants, and plants get their carbon from the atmosphere, right? Plants primarily get all their carbon from the atmosphere. Create this kind of link. So plant gets all their carbon from atmosphere. From atmosphere the plants gets their carbon. Now guys, what if I tell you, think about it, what if I tell you atmospheric carbon contains 1.5% C14 isotope. In the atmospheric carbon, there is 1.5% C14. That means all the CO2 in the atmosphere, it is mostly carbon 12. But 1.5% of all this carbon CO2 is made up of carbon 14. So guys, if 1.5% of all the atmospheric carbon is carbon 14, don't you think 1.5% of the plant carbon will also be carbon 14, because plants have absorbed it from the atmosphere? And 1.5% of our carbon will also be carbon 14. Tell me yes in the chat quickly, because we have got our carbon from the plants. So 1.5% of plants carbon is carbon 14, and 1.5% of our carbon is also carbon 14. Tell me yes in the chat quickly. Srinath, you have been able to understand? So can I say that 1.5% of our carbon, Sagar, Shritama, what do you guys think? Sagar, very good. So 1.5% of all the carbon that we have in our body actually primarily comes from the atmosphere only. So guys, if 15 kg is carbon, if 15 kg is carbon in the body, what is 1.5% of 15 kg? What is 1.5% of 15 kg? It is 225 grams. Let's consider it to be 200 grams. It is 225 grams, but let's say 200 grams. 200 grams of all my biomass, considering my weight is 100 kg, is C14, is radioactive carbon. 200 grams of C14 I have in my body always. Got it? I hope all of you understand. 200 grams of C14 I would have in my body, and I hope all of you understood this calculation. That means 200 grams of my body is radioactive carbon 14. Now when a person is going to die, there is no, see, when you take a living person, for a living person, the carbon is constantly exhaled. We are constantly exhaling CO2. So a lot of this carbon, which is supposed to be 1.5%, a lot of this carbon is being exhaled out. We're also leaving carbon in the form of sweat. We're also leaving carbon in the form of our excreta. We're also leaving carbon in the form of dead skin, dead cells, urine. All these are different waste mechanisms through which we are losing some carbon. So when you talk about living organism, the carbon 14 levels may fluctuate. In a living organism, the carbon 14 levels will keep fluctuating because we are keep eating food, we keep excreting out waste, we keep releasing some waste, we keep exhaling CO2. So the level of carbon 14 in a living person will keep fluctuating. A living person may not have a constant carbon 14 levels, but when a person dies, then this particular value will remain constant. When a person dies, this becomes constant because after the death of the person, there is no exhaling of CO2, there is no feeding of food, everything becomes constant. Everything becomes constant. Got it? This is 200 grams at the time of death. And now, when the Harappan civilization people discovered the skeleton of the woman, they figured out that this lady at the time of her death could have been close to 50 kilograms of weight. Why 50 and how did they find out? Actually guys, in our body, our bones, their thickness, their density is based on the weight of the body. If your body weight is higher, your bone density is likely to be higher because it is holding a greater body mass. So guys, we have something called thigh bone, femur bone. This bone density can help us predict the actual weight of the organism. How much weight this person would have had at the time of death by simply observing the thigh bone, observing the femur bone. Are you guys able to understand? Because this bone is the longest and the strongest bone. This bone holds majority of our body weight, right? Femur bone, we call it FEMUR. So by observing the femur bone, the scientists predicted that this lady at the time of her death would have had a weight of 50 kilograms. And now the scientists know 50 kg would have been the mass at the time of her death. So if 50 kilogram would have been her weight at the time of death, that means how much biomass? 15 kg biomass, right? And 50% of 15 kg, nearly 75%, 7.5 kg carbon, and out of this nearly 100 grams C14. Tell me guys, are you able to accept? Tell me yes, 100 grams C14 must have been there in this lady at the time of her death. Tell me, are you able to accept this? Tell me yes in the chat quickly. 100 grams of C14 would be there in this lady at the time of her death, right? 100 grams. So now we know that 100 grams of C14 would be there in the body of the lady at the time of her death, and we simply have to compare how much was the original C14 and how much C14 is there today. Suppose if we discover 50 grams of C14 today, 100 grams was there initially, but now only 50 grams are left. That means half of the C14 has already decayed. It means the specimen is at least 5,000 years old. Tell me yes in the chat, or if you want me to repeat, I'll repeat. If let's suppose we compare so 100 grams of C14 would have been there at the time of the death of this lady, and if we do the excavation and find out the current C14, and we discover that the current C14 says only 50 grams. So 100 grams was there at the time of her death, but currently only 50 grams C14 is left. Then don't you think we can easily predict that, okay, if only 50 grams is left today, it means the rest 50 has already got decayed, and the rest 50 gets decayed only when carbon 14 completes one of its half-life cycle, and that is for 5,000 years. So can I say, Shritama, what do you think? Can I say if only 50 grams of C14 is left, I will say that this specimen is at least 5,000 years old. Technically 5,753 years old. 5,000 years old. This specimen is at least 5,000 years old. Suppose if I would have discovered 25 grams of C14, that means one half cycle 50 grams, another half cycle 25 grams. That means this specimen is around 10,000 years old. If I would have discovered only 12.5 grams C14, that means 3 half cycles are gone. The specimen should have been around 15,000 years old. And that's how I simply have to compare the original C14 and the current C14, and I can easily predict where or how old the specimen is. Tell me yes in the chat if you guys are able to get it. All of you, come on quickly. If all of you have been able to understand, please write down yes in the chat quickly. If you guys have understood how practically we use carbon 14 dating. Right? So this is how practically we perform the carbon dating, and that is how it is done. I believe all of you guys are able to get it. So this is carbon dating and radioactive dating. And guys, the interesting thing is the Pune University professors found out that this particular specimen is from 2800 BCE. That means it was from the Harappan civilization. ये हड़प्पन civilization का specimen है. I hope all of you guys are able to get it. Right? That means a complete one full half-life cycle was not over. Right? So 2800 BCE was the age of this particular specimen. I hope all of you guys are able to get it and you have understood what is the meaning of half-life. But guys, the topic of half-life is not over yet. So when I talk about half-life, we have understood what is it. But the topic of half-life requires a little more attention. Guys, you should write down that the maximum age that we can decipher, or you can say the maximum age that we can calculate through carbon dating is 35,000 to 70,000 years. The maximum age that can be measured or that can be calculated through carbon dating is 35,000 to 70,000 years. You know why, guys? 35,000, 70,000? Actually, after 35,000 years, the amount of C14 left, it is so small that you cannot predict the right age after 35,000 years. Some specimens it can go up to 70,000 years but cannot go beyond that. So guys, my question is, if 70,000 years is the last age that you can decipher through carbon dating, then how do we know the age of specimens which are older than 70,000 years? See, we all know we have found the age of dinosaurs also, which have been there millions of years ago. We have found the age of great apes, which have been there 2.5 million years ago. So when it comes to age of organisms, carbon dating is one technique. But do you think carbon is the only radioactive element in our body? No, guys. Our body is full of radioactive elements. We have so many radioactive elements, like there is one radioactive element called iodine 135. It is a radioactive element found in the thyroid gland. ये आपके stomach, ये आपके neck और throat area के around होगा. This is having a half-life of 1 million years. Half-life 1 million years. There is potassium 40, K40, having a half-life of 2 lakh years. Uranium having a half-life of 4.5 billion years. Thorium has the longest half-life, 14 billion years, longest half-life. So guys, it's not just that you have to use carbon only as a specimen. There are many other elements around us which are in the radioactive form. Guys, mind my words, the world around us is full of radiation. The world around us is full of radiation, guys. It is full of radioactive elements. Everything around us is having some radioactive element. If I talk about this mouse, this plastic is having carbon in it, nitrogen in it. There is a chance that some C14 may be there in this plastic also. It is also radioactive, guys. If I talk about my mobile phone, it's a बहुत radiations already, you guys know already. If I talk about even this particular glass bottle, the glass bottle may also have radioactive substances. There may be some carbon 14 in it. There may be some potassium, may be some minerals in this glass alongside with silica, which may have some radioactivity. So guys, remember, the world around us is full of radioactivity. The human body is radioactive. The fossil fuel that we use is radioactive. Everything around us is radioactive. Some radioactive isotopes may be there always. Are you guys able to get it? This is what we have under half-life. So for other substances we can use half-life mechanism for others. Like for rocks, we normally use half-life of uranium. To find the age of rocks, we don't use carbon dating, we use radioactive uranium dating. Got it, all of you? So this is what is the concept of half-life. Please tell me yes in the chat if you guys have understood half-life. There is one small topic left. After that I'll talk about that also. Please tell me yes in the chat if all of you have understood. This is what is half-life. Got it? So the concept of half-life is clear, all of you? All right, perfect. Now I'm going back to the older slide. Look at this. The last topic is radioactive elements in nature. What all radioactive elements in nature are there? So in nature, how many naturally occurring radioactive elements we have? So I'm giving you a rule of thumb here. A thumb rule I'm offering to all of you. Please pay attention. So guys, remember atomic number 82. Atomic number 82. This is of lead. Lead is written as plumbum. Plumbum we call it. Why plumbum? Because the first pipes that were made for water transportation were made from lead. They were not made from iron steel. Lead was used to make the first pipes in the Greek civilization, and that's why the word plumber comes from the pipe, the person who cleans the pipe, plumber. So plumbum is word coming from there, right? So lead is atomic number 82. So guys, just remember this rule of thumb that all elements having atomic number greater than 82, all elements having atomic number greater than 82, like after this we have got element 83, that is bismuth, right? And likewise element 84, element 85, like this, all elements are radioactive. All elements, all isotopes are radioactive. So guys, you don't have to think. The moment you come across to an element that is having atomic number more than 82, it will be a radioactive element. वो radioactive element होगा. It will be a radioactive element if it has an atomic number more than 82. Okay. Lead is the last stable nucleus that we have in nature. Lead is the last stable nucleus that we have in nature, but beyond lead, all of them are radioactive. Of course, some of them have half-life of just few minutes also, but they are radioactive. In their own state, they will be radioactive. That is element 82. More than element 82, all of them are radioactive. Then guys, element less than 82, right? Element 81 is thallium, TL, thallium, TL, right? So element less than 82, for these elements, only some isotopes are radioactive. So it's not like all isotopes are radioactive, some isotopes are radioactive. Like, you know what, if I talk about iodine, iodine has got 32 different isotopes. Iodine has got 32 isotopes, and out of those 32 isotopes, 16 are radioactive, 16 are stable. Carbon has 3 isotopes, one of them is radioactive. Hydrogen has 3 isotopes, one of them is radioactive. I hope all of you get it. So this is what we have under the classification. So remember guys, nature, I'm writing this again, nature is full of radioactivity. There is everything around you is radioactive. Nature is full of radioactivity. But guys, whatever radioactivity that we have around us, jitni bhi radioactivity, whatever radioactivity that we have around us, we call it natural background radiation. We call it natural background radiation. So what is natural background radiation? It is the naturally occurring radioactivity that is existing around us, which does not harm our body. So when I'm drinking water, the water here may have some radioactive elements dissolved. The ceramic cup here may be having some radioactive element. If I drink water, I'm assuming, although you can't say about the quality of water these days, but I'm assuming that this water and this ceramic cup is having natural background radiation levels. That means the radiation levels are within the natural range. Okay, that is not supposed to be dangerous for our body. I hope all of you guys are able to understand. So this concludes today's class. Tell me yes in the chat and we'll call it off if you guys have understood. I hope all of you guys have been able to understand. And guys, mind my words, even if you're from science background, because there are almost 30-35% students from science background, you will still be able to learn something, right? Because see, UPSC is a completely different ball game, and that is where science also can become equally interesting, and it can also help us learn something even if we have studied science for so many years. Of course, the science students will have much more comfort in understanding those things, but I believe non-science students are also able to understand. Shitama, Sagar, what is your feedback? I hope you both are also able to understand whatever we studied today, right? So all right, thank you, Sagar. That's very nice. No, this is not the first class. Himanshu, the first class happened yesterday. The first class is there on YouTube, as well as you can talk to the admin. They have shared the link of the first class, right? If you are already in the group, Himanshu, then you can attend, right? Or if not, then you can go check out the first class on YouTube. It is there on YouTube. We have posted it yesterday only. You can talk to the admin. They will share the link with you. Okay. Yeah. So see, this is actually the reason why you are finding the subject of science easy is mainly because I'm not going into that boring part of science. To be honest, I'm not telling you numericals. I'm not asking you to do numerical practice. I'm only discussing concepts, and concepts are also being understood so that they help us practically. So why have I told you natural background radiation? Because you have to understand nuclear waste management. So nuclear waste disposal, you should know that okay, only that nuclear waste should be thrown out or should be disposed, whose radiation matches with the natural background radiation. That's it. So that's how the things are. So things in UPSC are highly practical, guys. So here everything that is going to be taught, it will have to have a practical approach. That's what makes science as interesting as any other subject, right? I hope all of you guys have been able to understand. So I'll be meeting you guys tomorrow. So I'll see you guys tomorrow then. All the best, right? Ecology students will be meeting today at 2 p.m. All right, all the best, guys. Thank you.